Welcome to homework.
All right, we are told that propanoic acid has reacted in the presence of an acid catalyst with an alcohol, and then we are given spectroscopic information about the product of that reaction. So we are told that propanoic acid is reacted specifically with methanol, MEOH, in the presence of acid to give something. And the spectroscopic information we've given is that the mass spectrum of this product has a mass to charge ratio of 88. Likely this is the parent ion. So maybe let's start there. Let's consider what the mass to charge ratio of the parent ion of our reactant would have been, so we can determine better what may have changed between our reactant and our product. So if we look at our reactant, we've got 1, 2, 3 carbons, which weigh 12 each, to give 36 mass to charge ratios. We've got 2 oxygens, which weigh 16 each, to give 32 to our mass to charge ratio. And 1, 2, 3, 4, 5, 6 hydrogens. 6 times 1 equals 6. So our original mass to charge ratio of our parent ion should have been 74. So we've increased our mass to charge ratio by 14. So let's just put that off to the side. We've added 14. Okay, let's consider some of our other evidence. We are told that this new product has an IR stretch at 1735 wave numbers. What occurs at 1735? Well, we know it's near the carbonyl stretch region. That is, it's a carbon, something on the other side. So our 1735 is in the region of carbonyl stretches. If we pinpoint it a little further, we'll actually see that 1735 is right about in where esters occur in terms of carbonyl stretches. That is, this IR is commensurate with a structure such as this. If we had an ester, we should expect that our IR spectrum would be around 1735. So let's call that another piece of evidence. IR suggests ester. All right, what other evidence do we have? We are told the H NMR spectrum. We've got something at 1.11, 2.32, 3.65. So the number of signals itself is a hint. We should expect to have 3 unique hydrogens based on our H NMR spectrum for our product. Well, what about our reactant? We also had 3. So something has changed, or we don't necessarily know evidence right off the bat that something has changed based on the H NMR spectrum and the fact that there's 3 signals. But we get additional information when it comes to H NMR. We don't just know the number of signals, we know how many protons each one represents. In this case, we know that the signal at 1.1 represented 3 protons. We know that the signal at 2.32 represented 2 protons. And we know that the signal at 3.65 also represented 3 protons. Furthermore, we are given the splitting constants, or the splitting values, as well as the shape of the splitting pattern for each of these. That is, we're told that the signal at 1.1 is a triplet, the signal at 2.32 is a quartet, and that the signal at 3.65 is a singlet. Let's set this aside for now, and instead of using this for predictive capabilities, we'll use this for verifying our answer. Because I think the final bit of information that we have that will be most useful is CNMR. CNMR tells us that we've got a signal at 9.3, 27.6, and 51.4, and 174.6. That's 1, 2, 3, 4 carbons, whereas previously we had 1, 2, 3 carbons. This tells me that it's very likely that we've gained a carbon somewhere, so that our product will have one more carbon than our reactant. Furthermore, if we look back at our mass spec, we gained a mass of 14. Our IR suggests an ester. That means if we started with propanoic acid, it seems very likely that we've ended up with an ester of that acid that has one more carbon than the original reactant. CNMR tells us we've gained a carbon. IR tells us that our product is an ester. We can use mass spectrometry and H NMR to confirm our answer. Does this make sense? Let's look at the mass to charge ratio that we would expect for this ester. We've got 1, 2, 3, 4 carbons now. 4 times 12 equals 48. How many oxygens do we have? We've got 2. 2 times 16 equals 32. And what about protons? 1, 2, 3, 4, 5, 6, 7, 8. That's 8 times 1. Gives us 8 for a grand total of 88. That's exactly what the problem told us was our mass to charge ratio for our parent ion. So it makes sense with the mass spec. Let's make sure it makes sense with the H NMR. We expect a triplet with a signal strength of 3 hydrogens. Well, there's 3 hydrogens right here. Does it make sense for them to be a triplet? They're neighboring 2 hydrogens. N plus 1 tells us that 2 hydrogens should give a triplet. Okay, we've got a signal with 2 hydrogens. That's a quartet. Here's 2 hydrogens. They're neighboring 3 hydrogens. So N plus 1, 3 plus 1 tells us that we should expect a quartet. Finally, we've got a signal of 3 hydrogens. That is a singlet. Here we have 3 hydrogens with no neighboring hydrogens, which would tell us that we should expect a singlet, which is what we've got. So all of this evidence matches up with us having received, or the product of our reaction having been, an ester derived from propanoic acid, the methyl ester of propanoic acid.